So welcome to the first video of online planning. This is online planning with discrete actions. Okay, so we are within our agenda of model-based RL, where we actually try to understand how we can make use of a model when we are training an RL agent. In the last video, we actually saw a few examples how to actually assist a model-based, a model-free agent, or in general, a reinforcement learning-based agent with a known model or with a model that we can learn jointly together while training. And in this video, and this video today, and in the next video, we will talk about online planning with discrete actions and continuous actions. But before we get started, let's first take a look about what do we mean actually when we talk about background planning or online planning, namely decision time planning. So this distinction is due to Sutton and Bartow's reinforcement learning and introduction. So basically, in background planning, we're using simulated experience to gradually improve a policy or a value function. So in other words, we use planning to gradually improve a policy of a value function based on the simulated experience that we obtain from a model. And the selection of actions is then based on the evaluation of the value function or the policy network. This is actually how we actually viewed that in the last video. And in other words, planning has played a major role in improving all table entries. So I actually tried to better estimate a Q function or to better estimate a value function, where this ST here or S0 is just one out of many. And we never really focused on the current situation our agent currently faces under deployment. So in other words, our optimization variables were some shared parameters theta that are basically the parameters that describe a parametric policy or a value function or something like that. And we actually trained this, in the end, we actually trained these parameters in expectation over all the available states. This is actually what we did in background planning, and this is actually very close to what we did in model-free reinforcement learning at all. In contrast to decision time planning or online planning, is conceptually very different. So in decision time planning, we use simulated experience to select an action for the current state. So we're never really trying to understand everything that happens around. We're just concerned with the current state we are in. So decision time planning begins and completes after encountering a certain state S0 in this case. So the computation is something different than the evaluation of a value function, and the output is some action sequence in this sense. So in this sense, planning looks much deeper than a one-step look ahead that we did in the beginning. So we actually consider a sequence of action, and we are optimizing over a sequence of actions depending on a certain state. So to put it formally, our optimization variables in decision time planning is actually a sequence of actions that we might take starting in some state S0 until our planning horizon, which is actually some goals that we want to end up in. So to put it in this way, what we actually want to do, we want to optimize a sequence of actions such that for this time horizon where we actually want to optimize, we want to get the maximum out of our discounted return. So in other words, we optimize only on a particular action sequence. So to put it conceptually, background planning, as in here, is maybe conceptually thinking of something like learning a set of habits, like general ideas or general behavior that you can just use when you need it, whereas decision time planning is something like a conscious improvisation in a particular situation. So actually this is really concerned with the current situation we're in. And we then can use them when we need them. This also puts something in context. So background planning is something that is usually very fast at decision time, whereas decision time planning is at decision time usually slower. And if we now see these two elements in here, so this type of planning that we can actually do, the question is, why should we use background planning over decision time planning or decision time planning over background planning? And there's a nice table that actually summarizes a few of pros and cons, or let's not say pros and cons, but some settings or parameters that actually hold for background planning and decision time planning. So when it comes to the to acting on the most recent state of the world, I mean, habits take a while to be updated as the world changes, and so actually this means that if we use background planning, we cannot act on the most recent state of the world because we actually need to update our internal belief on the state and our internal model. Whereas in decision time planning, when the state of the world changes, we can immediately plan based on the most recent state. So this is actually why decision time planning acts on the most recent state of the world. In a sense, as we're not learning any policy or value function or anything, with decision time planning, we can actually act without learning at all. So we will see that you can actually come up with an action plan without having learned anything yet. So you actually can take a learned model or a learned physics model, and then you can use this based on the current situation and a time horizon. You can actually use this model together with the environment to actually come up with a plan and just execute your plan without learning anything at all. Whereas in background planning, you actually have to learn through the interaction with the environment and your model to actually how to actually solve or how to actually behave in the environment. So about competency in unfamiliar situations. So in a sense, if you end up in a setting that you haven't seen in training, your policy or value network might not really have a competence in such situations. So imagine that you're playing, some hard exploration games where you actually need to grab a key to open a door or something. If you have never encountered the situation of having actually a key, you will not actually see a situation where you can open the door. And this is something. If there's an unfamiliar situation and you use background planning, you're pretty messed up in a sense because you really did not know what to do with that situation. So actually, the problem is even further. So you will not even say, "I don't know what to do." You will rather select any action that makes no sense at all. Which in this case, then decision time planning is much better because you can actually take the current situation and plan what to do and explore or exhaustively search the state space and can actually search through good action sequences. So dependence on the observation space. As we have seen also in previous lectures, in background planning you usually need an encoding of your state space or a description of the state space in order to come up with a good policy or value function. And the question is, it's often not very easy to come up with a well-defined representation of it. So in background planning, in a sense in here, there must be some encoding or description about how your state space is defined. And the question is if you have a vision system or your robot just behaves based on a camera image, the question is, do you take the pixels? Do you embed a graph? Or do you embed a graph out of this? Or do you extract joint angles? What is actually the state space and the state encoding? And turns out that a proper state encoding is very crucial for successful learning. In fact, it turns out that in decision time planning, you don't even need a state encoding because you're just optimizing over the action horizon and you try to estimate what your world is giving you, and you do not really need an encoding of a state. So the performance of decision making crucially depends on how we encode the state, and you will see that this is very crucial. When it comes to partial observability, in fact, decision time planning assumes a full state information, which is really rarely the case. So actually in decision time planning, you really need to know where you are, and this cannot always be satisfied. Of course, there's mild assumptions that you can take, and then you can actually assume that you have an observable state. However, this cannot always be guaranteed. In background planning, you usually can come up with a strategy to do this. When it comes to computation and deployment, so in a sense, what you can also say is in background planning, as we are optimizing for all possible situations and we're learning a set of habits, there is a lot of computational effort involved in the training of the agent, which is actually something before deployment. However, in decision time planning, most of the effort is actually most of the planning and effort is actually be taken at deployment, which actually makes them much more computationally expensive after deployment. Predictability and coherence. In background planning, usually you act with a regular behavior, such as a footstep, which you cannot really come up with in decision time planning. And what's also the case is the discrete and continuous action spaces. In this video, we actually talk about discrete action spaces, and in the next video, we will be talking about continuous action spaces. While this is not really that much conceptually different in model-free RL, although there is a difference. Here, we're really talking about two completely different classes of algorithms. So model-based RL is, there's a set of algorithms that's completely different for discrete state spaces and for continuous state spaces. So usually the guts or the core of the algorithms is the same in background planning algorithms, while in decision time planners you really have completely different algorithms. Okay. So let's get started. So this was actually the general introduction to online planning. Let's talk about discrete actions first. So as I already said, the distinction between do I use discrete or continuous algorithms to do model-based RL is not really a choice that you can make on your own. So it's actually defined by the problem. So there is discrete settings like games or treatments in medicine, or things like this, and there's continuous settings that usually involve something with robotics or muscles that are by design continuous, and this also restricts you in the kind of algorithms that you are able to choose in order to solve your problem. So let's talk about the setting of discrete actions. So what are, for instance, environments with discrete actions? Usually we have problems with discrete actions, which are games, supply chains, production, and optimization. And most of them have in common that their dimensionality is so large that it is impossible to enumerate all the solutions. This is also something that we have seen when we motivated going from explicit tabular value function representations to value function approximation, where we actually said that there is so much states that we can where we can actually end up in. We cannot enumerate them to actually store a Q value on them. And this is the case for maybe any real world application that you've seen so far. And a very famous example, of course, is games, because in games you have fast simulators and you have large state spaces, so you can really benchmark your solutions in a fast way. And two very popular examples is, for instance, the game of Go, which we will also cover in this lecture, and also, of course, things like chess, where you have a discrete setting with a large and not enumerable state space. Okay, let's talk about the main algorithm that we use to solve discrete action spaces with model-based RL. And the main algorithm behind this is Monte Carlo tree search. This is actually the most popular algorithm that is embedded in modern online planners, and maybe in fact it is also the workhorse behind AlphaGo and all the derivative work that builds on top of it. And the definition is simple. Just assume that you have this kind of tree, and states are the nodes, and the edges actually. And you are in a state, and edges take you to another state depending on an action. And the action is actually the arrow here. So the edge and the arrow is the action takes you to another state. all the and I mean, you saw that this is something like these backup diagrams that we also talked about in the beginning, although we didn't really dig into them too much. So you saw the backup diagrams, you had states, and you traversed the states through taking actions. And we somehow wanted to estimate a value function or a Q function. And the idea of Monte Carlo tree search is that as long as you have your tree, so your tree somehow encodes the knowledge. So you actually estimate for all of the states in here and the actions, you estimate the value of each of the states. And as long as actually you have subsequent nodes in the tree, you can just select the action that maximizes your return. You take this action and you end up in the next state. You do this all over again until you actually end up at a leaf where you actually don't know what to do. And at this point, so the first thing is the select. So you actually select an action based on your current knowledge, which is the current representation of the tree and the associated state values of these nodes. And you do this until you reach a leaf node. And if you reach a leaf node, you actually do not actually know what next action you need to select because you don't know any much. So at this point, you expand the tree. You will see this in the upcoming slides. What do we mean with expanding the tree? We just look at all the actions that we can take and expand the tree with certain nodes. And from there on, we do simulation. So we take a so-called rollout policy where we do simulation from there onwards in order to estimate the true value of the expanded node. So this is actually as we do not know what's happening below there, we actually expand all the new. Or just imagine that these are the expanded nodes and we do not actually know their value. Well, what we do is actually we start from here and we simulate a bunch of trajectories until they end, and we use that in order to estimate the value of this state. And so we do a simulation. So actually also meaning that we need to do a simulation and we need a way to do the simulation. And if we actually did a lot of simulations, in the end, we actually can average all the values and we have an estimate of the value of the state. And if we have an estimate of the state, we can back up all the information to the head of the node in order to get new information. And yeah, so the tree part is very simple. So the tree part is simply this is the backup, and we start over again. So Monte Carlo tree search. So the tree search part is really simple. So we select and traverse. So we search around the tree, and the Monte Carlo part comes in when we do the simulation about here. Okay, so let's go through these 4 steps explicitly in the next slides. So the first step is the select step. So the question is, how do we actually do a selection in NLP? We follow some search policy bias. It is not that trivial actually to just select the action to go down the tree, because we actually have seen also in other examples that we have an exploration problem. So we might have information on this tree, and it's not always a good idea to take the maximum action in here. So what we actually do, we select an action based on the estimate of the value of the successor states times some computation, and the computation just, you will see this in the exploration strategies video. So in fact, usually what it is based on, it's based on the upper confidence bound. It's a Bandit's algorithm that formally defines how to do exploration in such settings. And what you actually do is you sample an action that gives you, on the one side, the highest expected value. So the state is maximized. However, also the visitation count of all the states. So you try to balance a little bit your current estimate of the state value and how much information you already got from all the possible leaves starting from this node. So this is actually what you want to do. So you sample an action and you make it based on the estimate of the node. You have a tunable exploration parameter. You have the number of visits of the parent node and the number of visits of the node y in here. Okay, and you actually do this until we reach some leaf node, which is in here. So in this case, we would go from here to there, from here to there, and from here to there. And from now on, actually from here, we do not actually know what to do next. So we have a leaf node. The episode didn't end yet, and the question is, what can we do? And as you might already remember, we expand. So what we actually do is, so as we know the transition model, so we actually also know where actions lets us end up in, or we do a bunch of one-step simulation to actually get knowledge about it. But just assume that we know it. Then we can actually enumerate all the successor states given the actions that we can take. So this is the expansion step. It's rather trivial, right? The next step is actually the simulation step. And the question now is, how can we get an estimate of the value of these states? And this is actually where the Monte Carlo part comes in. So what we actually do is we randomly choose one of these new child nodes in here. And from here on, we just play randomly. So we just take a random policy, we call it random rollout policy pi r, and we play this random policy until the game ends. Until the game finishes. So in this case, we run a bunch of simulations starting from all the child nodes. Just select them, and if that goes along, we do all these Monte Carlo rollouts. And what these Monte Carlo rollouts actually give us is some information about what are the Q values of all these states and actions in here. So just remember, as we did a very bad policy in here, so we just took a random rollout policy pi r. This Q is an estimate, but it's like something like a lower bound estimate on Q. So if we would have taken a good policy in here, we might end up with larger Q values. But it somehow gives us some information about the lower bound of the Q values. And okay, so depending on how many rollouts we actually simulated, we can actually come up with a good estimate of our Q values of all the leaf nodes. So in here. So, and what we actually now can do is, so as we have more experience from these nodes, we can back up all this information all the way up to the root node that we actually stand it up in. Okay, so in fact, we now learned much more about the tree. So actually we get more information. We took one step further down the tree. We got new Q values. These Q values might give us new knowledge, and this new knowledge can be backed up towards the top. So far, we actually used two policies. We used the selection policy pi s. That is actually used in the selection step. And this selection policy pi s usually uses the Q values that we already have knowledge about. On the other side, we have a random simulation policy pi r. So depending on the leaf nodes, we don't know what to do, so we take the random policy. And however, while we did this randomly in here, we now gained information that we can actually use to improve our selection policy pi s. So in fact, our selection policy pi s is getting deeper and deeper throughout all the iterations of our algorithm, and with time it will get more and more accurate with being backed up the information all of the leaf nodes all the way to the top over the iterations. So this is actually how with Monte Carlo tree search we actually come up in the end with a selection policy that is a pretty good estimate of what we actually want to do. Okay, just to sum it up a little bit, Monte Carlo tree search is a planning algorithm, and we either need a transition model to run it, or we need a way to do the simulation. So we need some way of actually getting to know what's happening in the system. But also the question arises, when should we actually stop? So we could run this forever and ever, and the question is, when are we done? So in principle, we could run MCTS forever. However, it also depends a little bit on how you want to integrate the planning and the execution of the model. So what you usually do is you're having your agent deployed in the system and you are in some state ST. What you usually do is you run MCTS until the convergence starting from the current real world state, and then you take the best action in the real world. So the best one action in the real world, and then you go back to one and start over again. And what you usually can do is, or what you've usually been doing, you just specify a maximal computation time per MCTS run. This is what you usually do in practice. It's very easily implementable. Or you can also, if you have time, you can also solve the whole MDP and then run the tree greedy in the real world. This is also possible if you really have enough time to do all this. One more thing about the rollout policy pi-r. The selection policy pi-s is the Q value of being greedy in knowledgeable states. So actually, if you know enough about the states, pi-s is a good approximation of what to do. However, it's under the assumption that we behave randomly in the simulation, meaning that we underestimate Q. So this is just something you need to know. So you need to run MCTS for some while to actually get a good estimate of the real Q values and hence a good selection policy pi-s. And there is also another way, another thing to mention. There is important side considerations with the encoding of goal and success conditions and fail by termination, so constraints. So there's conceptual difference between do you get through certain actions, do you get a reward, or do you get a reward by not doing anything? So this is something that's really hard to encode in MCTS applications. So imagine in Pac-Man, you might easily recognize that eating dots will give you a positive reward, while avoiding ghosts is something that you need to do to be alive. However, if you're successful, you will never encounter a ghost. And this is something like really hard to implement properly in such a system, which is called actually a constraint. So we actually encode constraints, and this is something a little bit tricky to implement. So actually you want to modify the rollout policy a bit. So in this case, the rollout policy might not be a completely random policy. You might have some constraints like trying to staying alive as long as possible or something like this. So the question is, also people ask me a lot, is this reinforcement learning at all? So why is it reinforcement learning? It's just clever search. Yes, it is, and no, it is not. In principle, it's a policy search algorithm, and you can see that, like, also you might also encounter similarities to A star or something. However, so the tree traversal and things like this is like a tree search algorithm part, and the RL kicks in when we talk about the backup of the Q values. Okay, so let's talk about MCTS in practice. Let's talk a little bit about AlphaGo and its derivatives. So this is a nice graph that actually shows a little bit the evolution of AlphaGo. So we started with AlphaGo in the beginning. Then on top there comes AlphaGo 0, Alpha 0, and Mu 0. And we will actually introduce all of them in the upcoming slides. So let's start with the original version of AlphaGo. So maybe some of you actually know Go. In Go you have a board where you actually play stones. They could either be white or black. And the problem in Go is that the game of Go has a large breadth and depth of the episodes. Meaning that in terms of breadth, this is actually the average number of legal moves per position. So you have actually a lot of positions that you can actually do. And the depth of the tree is usually around 150, which is actually the approximate game length that you can actually have. And so you can actually use MCTS for this because actually it's a discrete problem. You cannot enumerate it, so it's like perfectly fitting to Monte Carlo tree search. And the main idea of AlphaGo was to enhance Monte Carlo tree search with a learning component. And to do this, we actually have two main networks. The first one is the reinforcement learning policy networks. These policy networks, what they actually do is they are just trained to select actions. So it's like a policy network. A policy network gets as an input a state, and you select an action from it. And there is another network, it's the value network. And the RL value network just predicts, given the position, the probability of winning the game or losing the game. So this is actually the two components that interact with each other. And there's a tricky way of initializing them. So in the beginning, we what we actually use to begin with, or to keep the ball rolling, actually, we train the policy network in here. So actually, the network that takes in board states and outputs an action. We train this using human expert positions. So in these cases, they actually took positions of the KGS Go server. This is something that already existed before, and they randomly sampled state action pairs from human expert moves. So it was like through 30 million positions from the Go server, and they ended up in using a 30-layer neural network that uses conv layers and ReLUs, and they actually had an accuracy of 57% in selecting the correct action, which is already pretty amazing. However, it turns out that a 30-layer neural network is maybe not the best. So having a 30-layer neural network with a high accuracy of 57% may not be the best idea, because it actually takes a lot of time to actually do the forward pass. And as we do multicolored tree search, we rely a lot of simulation, and we do these the simulation steps, which requires a lot of computation time. So what they actually did is, they came up with a new policy network, PI, which is the rollout policy network. And what they actually did is they initialized it with the same data. And however, what they did is they used a much smaller network. So their network only uses a linear softmax and small handcrafted input features. So no conv layers or something like this. And as this network is much smaller, of course, it only has an accuracy of 24%. However, the forward pass only takes 2 microseconds in here, instead of 3 milliseconds from the supervised learning policy network with the conv features. So what they really did in here is they trained a small version of the policy network just to make fast inference on the selected board states. Okay, so the question now is how to come from the human expert positions networks to the safe play position networks. And from here, they learn a policy network P-row. And what they actually do is they play self games with this policy network against the random ancestor of this network. The reward is being 0 everywhere, and it is plus and minus at the end of it, depending on the outcome. So actually, if this agent using this policy network wins the game, it gets a +1 reward, and if it loses, it gets a -1 reward. And for all the other steps, it just gets 0. The policy networks are getting improved with policy gradients, and doing this already yields a very strong player. So if we just do this, so we take this policy network and improve it using self-play, we have 85% winning probability against PH, which was actually in 2016 one of the strongest open source Go programs already. So this is actually already a very good thing to do. Another component is actually the value network V theta. The value network, as we usually do, as we usually use such a network, is used to approximate the value function under the policy pi row. It's just the same neural network architecture that we use for the RL policy network in here, but it outputs a single value. And the single value is just the probability of winning. And it uses the state outcome pairs, so state and what was the outcome, and it's just trained using standard stochastic gradient descent and a mean-squared error loss. Yeah, so actually this is done using a simple value network trained with MSE, and because actually, why do you do this? Actually, the question is, why is that helpful to do this? So actually, if you do, the question is, how good can you perform? How can you actually grade a board state depending? So what you usually do in MCTS, you run all the simulations. However, if you run all the simulations, this takes a lot of time. And what you see here is that let me just make it a little bit bigger. that the mean squared error, if you do this over the simulation, it takes a lot of moves to actually go down and really reduce the mean squared error of the value network. And you see that using all the other policy networks as a baseline and as a way of doing it, you can go a lot faster. And what you also see is that the fast rollout policy in here, it has a higher mean squared error, but it's not that significant. So actually, as you could do a lot of more computation than with the original network, I mean, it's something like 50,000 more computations in the same time, you can do a lot of more moves in the same time, which means that using the fast rollout policy is a very good approximation to use to train the value network. Okay, and then we do the MCTS part. So as in the beginning, we have the selection. So in nodes that we have been visited before, we select which action to take based on the RL policy network, action probabilities. So there is actually the action probabilities, and we select the actions based on the RL policy network, and we approximate the Q values in the tree using an upper confidence bound bandits like process. It's a little bit different from what I told you in the MCTS, because they actually directly integrate the exploration bonus in the Q value. But you can actually look up the actual update function in this paper in here. In the expansion step, so when we reach a leaf node, then the supervised learning policy is used to assign a prior action probability, and we actually expand the tree according to the most probable action of the RL policy network. So then we do the expansion step, and after the expansion we do run multiple simulations all in parallel, and this we do using the fast rollout policy, and we do this until and all of the simulations threads we run until the game finishes. Yeah, and how do we actually train the networks? So the value of the previous leaf nodes that has been expanded is updated using the combined RL value network and the final average reward from all the rollouts. So we take the average of all the rollouts, and we update the leaf node, combining them together, and we update the Q values and its visitations of the tree nodes as in the classical MCTS algorithm. So if you're curious a little bit about how this works in general, there's a small section in the paper that explains it very well. If you're curious and if you're interested, just look it up. And interestingly, all the games are played against the previous reinforcement learning policy as an opponent, so it's completely self-play, starting from the supervised initialization in here. Okay, and during deployment, we just run online MCTS. So with the board position that we see, we just run MCTS until our computation budget is exhausted, and then we take the action that maximizes the return. And if we encounter a new board state, we just run online MCTS again. Okay, so this was the original AlphaGo implementation. So let's talk about AlphaGo 0. You see here that AlphaGo 0 is still like applicable to the domain of Go. However, it doesn't require human data and no domain knowledge, and we will see how this is actually implemented. So in AlphaGo 0, there is 4 main differences to AlphaGo. The first one is it is trained solely by self-play with reinforcement learning. It starts from a random play without any supervision or use of human data. The second is we only use black and white stones from the board as input features. So in the beginning we had complicated versions of extracted features or convnets, depending on the rollout policy network that we use. In here we take the black and white stones from the board as input features. So it really boils down the problem to relevant things. So no handcrafted features anymore. There is only a single network instead of 2 separate policy and value networks. So there was the value network and RL policy network, and these were 2 distinct networks. However, they share a lot of information in the early layers. And what they did now is they just replaced it with a single network that has two heads, one for the policy head and one for the value. And there is no simulation rollouts during deployment because we rely only on the networks. So it's like something like a simpler tree search that relies upon the single neural network to evaluate positions and sample moves without performing any MNC rollouts. Okay, and the self-play is always against the strongest version of the policy and value network and not about a random ancestor. Okay, so so we use the MCTS also in training. We train the RL policy head of the network to mimic the powerful MCTS during policy training. We train the RL value head of the network to predict the outcome of the game, as we also did it in AlphaGo. And you can think of it like something like distilling the power of Monte Carlo research during the training of the policy and value network. If you are interested in how this actually works in practice, so the paper doesn't give you so much information. However, I found this nice AlphaGo Zero cheat sheet that you can also find in this link, where you can zoom in and dig a little bit into the details of AlphaGo Zero. Another iteration on AlphaGo and AlphaGo Zero is AlphaZero, where they actually expanded it to different domains. So while AlphaGo and AlphaGo Zero, as the name suggests, are only applicable to Go, they came up with AlphaZero, which is actually a little bit of agnostic to the game, so it can also be used with Go, chess, and shogi. So there's no specific game knowledge encoded. Which also means somehow that it's like something like the smallest technical jump between all the versions. So the main difference of AlphaZero to AlphaGo Zero is that AlphaGo Zero expands AlphaGo to other games, as the RL policy and the value networks in AlphaGo and AlphaGo Zero actually exploited some of the Go rules. They augmented the data since the Go board is actually invariant to rotation and translation, which is not the case for all of the games, and also a thing that Go games can end with win or lose, and there's no draw like in chess. And AlphaGo actually, or AlphaGo Zero actually exploited this to estimate the probability of winning, which is something that you cannot do if you want to be more open to other board games. And also, self-play is now against the current version of the networks and not against the strongest players so far. So it's against the same version. Okay, if you're really interested in how this works, there's a nice hands-on video that you can look up in here, where you actually have a small piece of code, like a one-dimensional game, where you actually where you need to select two nodes. And he comes up with a nice implementation and a description of how to actually implement AlphaZero and Monte Carlo tree search in a nice Jupyter notebook. And I think also the code is available in here. Okay, so the final iteration is actually MuZero. MuZero is a very recently proposed algorithm, and it also has been published by Nature in last year. And in MuZero, actually, we do not assume zero-sum games that win or lose, but we actually assume a more general reinforcement learning structure with having rewards. MuZero uses a little bit a different approach to overcome the limitation of the previous approaches, because instead of trying to model the entire environment, MuZero just models the aspects that are really relevant to the agent's decision-making process. So, in a sense that, or put it differently, instead of using, while the policy is still computed over Monte Carlo tree search, we use a learned model instead of game rules in this case. And the learning actually we learn actually three components. We learn H, a function that transforms the observations to latent states, which you also have seen in the last video how we can do this. We have a model G that actually models and predicts the next latent states on the rewards based on the current latent state in action, which is something like a forward model or dynamics model. And we have a function that predicts the current policy from MCTS and the value of the latent state. And the interesting thing in here is that all components are learned end-to-end using a real game data stored in a replay buffer. So the idea is that in Mu0, you do not need to model aspects that are really important. You do only need to model aspects that are really important to the decision-making process. And the general idea or the motivation behind it is that, or actually this is how they actually motivated it, knowing that an umbrella will keep you dry is more useful to know than modeling the pattern of the raindrops in the air. And this is actually the motivation behind them. They actually want to learn the model, and they want to learn the components of the model that are really important for your decision-making process, and they do not want to focus so much on the things that are not so important for your decision-making process. So this is it for online planning with discrete actions, and in the next video we will talk about online planning in the continuous action space.